So, hi everyone. So today I'll show you a third way to do directed type theory, but this time with a very different tool, and it's not going to be dependent also. And the idea is dinaturality, dinatural transformations. So as you've seen now, REFL and J allow you to derive symmetry. Directed type theory should be whatever that is that allows you to interpret, as with types, categories, right? So types are categories, terms are functors, the points become the objects of a category, equalities become the morphism, and then you have home types in your semantics. Now types have a polarity and equalities have directionality, all neat and fine. Now semantically REFL should be the identity, but as Fernando showed it to you, well, I'll show you later. Now transitivity of directed equality becomes composition of morphism, okay, that's also pretty reasonable. So this is what your rule should be, right? So J allows you to get stuff for free. So you would expect that you can get something like this, right? So you want to prove this down below, and it suffices to prove it in the case where A and B are the same. Now, as Fernando was telling you, directed type theory is not so straightforward. For example, in the case of REFL, you use A here on both sides, but home takes a contravariant value on the left, right? So it doesn't really make sense. Here, you have the same problem. Here, you have B of type C, and then here on the left, you must use B again, but it doesn't have type C op, right? So one solution to this by North is to instead use C core, which is the maximal subgroup of C. Now, then you also have a J rule for this, right? Can you do better? Can you do without groupoids? For example, with two-sided dependent fibrations. But today I'll show you how to do this with dinaturality instead. So I'll show you a first order non-dependent directed type theory. So the entailments are proof relevant. With this semantics, the types are categories, contexts are product of categories, terms are functors. And then you have predicates, just like in first order logic. And these are interpreted as Dipre sheaves, so functors from C op times C into set, among which you also have home functors as an example, which plays the role of equality. And then your entailments are going to be dinatural transformations, which are a generalization of natural transformations, and then your quantifiers are going to be ends and quants, which is a folklore idea that everyone in category theory knows, that they are kind of like quantifiers, ends and quants, but that hasn't really been made logical or formal either. Dinaturality allows you to solve the variance issue without groupoids, and tells you also semantically what those restrictions on J should be, and tells you where they come from, to avoid symmetry, but obtain all the other interesting stuff on your equality. Exactly. Then we're going to give logical rules to these two quantifiers. Ends are for all, quants are exists, as the directed quantifiers of directed type theory, which is also an interesting question. What should the directed quantifiers of this model, the category model, be? This is one answer. And these rules allows us to give proofs in category theory, just like Jacob was showing you before, in some way, with home interpreted as equality, logically. And we do the first order part mainly because we are interested in quant calculus, which is also another folklore thing that MacLean already knew in 1997, which is also typically first order, so we want to capture this, at least. So we have a judgment for types. If C is a type, C op is a type, product of types, functor, category here, and the terminal category. Again, I'm saying these words because types are interpreted as categories, all pretty reasonable. Then you have a definitional equality, which are isomorphisms, which it just distributes over everything in the nice way possible. Then you have context, which are just these types, and also C op is a context. That's also reasonable. Then the semantics of context is they're just products of categories. So you take the product of the interpretation of each category in the context. Then you have a judgment for terms, which are just simply types. There's no type dependency here. Terms are just functors from gamma into C. And here you just have the usual stuff you have also in simply typed lambda calculus. For example, you have variables, you have the functor into the terminal category, the product of two functors in this sense, the projections are functors. And then you have that if you have a functor from gamma into T, you also have a functor T op. It's also pretty reasonable. And also a definitional equality on terms such that T op is equal to T. Then you have a judgment for predicates. And the semantics for these are going to be exactly Dipre sheaves. So functors that take both a variable from gamma op and a variable from gamma. Then you have these formation rules, which are reasonable. You have conjunction, which is interpreted as the pointwise product of Dipre sheaves. You have implication here, which is the pointwise home in set. Then you have the terminal, which is the constant in the singleton. And then you have these two, which take the coend and the end of these endoprofunctors in set, which you interpret as existent for all. Now, the interesting part, directed equality predicates. The idea is that this is a proposition, so a predicate, if you have S and T terms which are typed not in gamma, but in gamma concatenated with gamma O. That's the key. So you're allowed to use in S and in T, which you can also pick the variables, using both the variables from gamma O or from gamma. That's the key aspect. And whenever you pick a variable from gamma O, we're going to put a little bar on top, just to remind us of that. This allows us, for example, to write some interesting terms about equality. So this is just to write them in. So an entailment is what you imagine. I'll show you that later. But REFO, for example, is just defined like this. And here I'm using the variable x from gamma O. Here I also have the beta, the b from the other context. And for the case of symmetry, like Jacob was saying, you have to put these two negations here. And that's what we do. We have these contexts here. So just some terminology. In the first case, you have two positions, and positions have polarities. Positive when you take variables from gamma, and negative when gamma O. So this is a negative position, this is a positive position, this is a negative position, this is a positive position. Here there are 6 positions. And variables have variance. A variable is natural when it's always taken from gamma, and it's dinatural or mixed variance when sometimes from gamma, sometimes gamma O. For example, REFO x is dinatural because it's taken with both polarities. But in the composition example here, transitivity of directed equality, B is dinatural, but A is natural. It appears here negative and here negative. That's perfectly fine. Same thing with B, with C, sorry. It's positive, so it's also natural. Then you have a judgment for entailments, where phi is just a list of predicates interpreted as the pointwise product of the sheaves. And the idea now is that I'm going to write them like this to indicate that you have both the negative positions and the positive positions in entailments. Semantically, these entailments are interpreted as dinatural transformations. And now the key idea, if you remember, these are functors that take a contravariant variable and a positive one. And the idea behind dinatural transformations is that I'm going to take families of functions in set for every x that I use in the semantics, both on the left and on the right side at the same time. I don't care about polarity in the model. That's the key part. And then a certain equational property holds for these families here. The problem is that this equational property is not compositional. It's a standard thing. Now, these dinaturals that I indicate with these 2 dots here that you put in the middle, they always compose with natural transformations, the one you know and love. So this situation happens in the model. And this is how you capture it. Now, it's complicated, but the idea is that you have a phi, and you can derive p, and here you can derive p, and from p you derive q, and then you can just compose these two. The thing is, you have this restriction here. You also have that p and q don't depend on gamma. You can make them depend on some bigger context, not too important here. But this is a rule that axiomatizes precisely composing on the right. There's also one that composes on the left, and you ask for associativity. It's all nice and dandy. So it's a bit complicated, right? I'm not going to explain it too much in detail. But the point, the takeaway here is that whenever you need them to compose, they do. In every practical example that you care about mostly, that I'm going to show you now. Now, here are the rules for home, the ones we care about. You have an entailment into home, xx. Now I can use xx. And I just need to provide a family of functions instantiated on the diagonal. So this family here is dinatural. In the model, these two are going to be equal. The bar is going to disappear in some sense. So this entailment exists because you have identity morphisms. So it's exactly the semantic justification we wanted from the beginning. And then here's the key part. Here's how I'm going to tell you here's the J rule. This is what it looks like. And this holds in the model. And the key aspect that you need to focus on is that in the conclusion here, A bar and B bar do not appear. And here in the premise, A and B used positively do not appear. You only have the negative ones. So the way to read this is that if you have a directed equality E here in context, I can contract this equality only if A and B appear positively in the conclusion, only negatively in the context, And from this, it's enough to prove that P holds on the diagonal Z, as it is here, also in the context. So this is the syntactic restriction. Why is this validated? Just functoriality. There's no dinaturality yet. From this example, you can already derive this map, transitivity. So if you want to create a map like this, and it's enough to just give a map like this. Why can you contract it? Because A and B only appear negatively in the context. A does not appear negatively, B appears negatively. And positively in the conclusion, B does not appear negatively. And A appears positively, so it's fine. Then you can prove some other things. So for example, if A is directed equality in some sense to B, then FA is equal to FB. It's like some congruence. And this semantically means that F is a functor as a term. And then you have transport, which just means that predicates. Now, I gave you this example with only one variable. You can also do it with two, that you can transport points along a directed equality. And symmetry is precisely what you do not get. The syntactic restrictions tell you that you cannot contract this E and also have that B bar and A bar become the same. That's why, because A and B must only appear positively in the conclusion. So you're exactly doing the kind of thing that the rule forbids you. So semantically, you cannot prove this in exactly the same way that Jacob told you. You just pick a type that is not a good point. Then you have a final judgment. It's just a movie. A judgment for equality of entailments. Why? Because the natural transformations are families of functions in set, which can be different. This is not a logic, it's proof relevant. So you have a judgment like this, and this is an example of a rule. It's exactly the computation rule for J. What does it tell me? It tells me that if I have a map that is constructed with J and I pre-compose with REFL, which I can do in this case. I told you that every time I would compose with these square brackets, it would be fine with the dinaturality business. This is equal to the H that I use J on. So kind of miraculously, it works with these brackets to compose. And some examples, you have that composition on the left is equal to G. So because I contracted the one on the left. So this is the same steps as in Martin-Löf type theory. And same thing here with using the functoriality of terms. If you apply congruence on REFL, you just get REFL back. What if you want to prove unitality on the right or associativity? This is where the naturality comes into place. So there is a dependent version of J for equality of entailments. So it's kind of like J, but it works on the judgment of equality. So this is how it works. If I want to prove that alpha is equal to beta, and these two alpha and beta have exactly the kind of restrictions that allow you to apply J, then it's enough for these two maps to be equal on the diagonal and to be equal on REFL. This is the key component. The semantics works only because of dinaturality, only because the entailments that we pick are the dinatural ones. And this has a very Yoneda-like feeling, right? So if you want to prove that if you compose on the right with REFL, you have an equality here in context, F, which now I can contract because these have exactly the shape as J, maps you construct with J. And so I have REFL here. I want REFL here, and these hold by the composition, the computation rule for J. To prove associativity, you do exactly the same thing. You have these three equalities. You contract the first, then you have REFL here, and then these compute, and it's all fine. Entailments, you can also prove internally that these must be natural transformations. You can also prove the natural transformation. So if you take an entailment where X bar does not appear, this semantically is just a natural transformation. If you want to prove that this is a natural transformation, you do some transport business, which is exactly functoriality. This is the naturality square. Why is this true? Because F here, I take REFL, and then the rest follows by computation. I just get back to this case. So you see that I get naturality for free, which is exactly what Fernando was talking about. But again, this is not a dependent type theory. This is just a logic in this sense. And this also works for naturality because transport is a natural, so you can compose with transport. It's a natural, exactly the right shape. And terms also are natural transformations. For terms are also naturals. So in the model, a dinatural like this is precisely a natural transformation. And you put exactly the definition here for the naturality square. You have f, again, you just put REFL, and then things followed by computation. That's exactly what you would expect. And also you can internalize these families inside the theory by doing some business with ends and coins. So in this case, with ends, you can internalize natural transformations. If you know category theory, this is pretty reasonable. This is a natural transformation from F to G, and this is a natural transformation between predicates. And you can also do the same kind of internalization for dinaturals, but we don't care too much about that now. Great. Now, logical rules for conjunction and implication and quantifiers. These rules here are validated in the model. So what this tells me is that if I have a dinatural with this shape into the pointwise product of the deeper sheaves P and Q, I get exactly a pair of entailments. Pretty reasonable. And now you have a rule like this, and now you have a rule like this. What I want to focus on is the fact that this rule is in some sort of adjoint form. It's expressed as an isomorphism. That's the key point of adjoint form. An isomorphism of stuff. The rules, like the later rules, are also like this. Now, this one is particularly important. This is called twisted exponential. And it basically says that I can curry dinatural transformations, and it's perfectly fine. With naturals, this is not possible. You don't get a natural transformation by currying one side to the other. So if you have a family like this, you can just take this A and put it on the right side at the cost of inverting the polarity of every position. So if X bar was here, you have X, and X becomes X bar. That's the price you have to pay. Then you have these rules for ends, which basically say that a wedge is the same thing as an arrow into an end. And these rules for coends. And these are all, again, in adjoint form. This is because it's a restriction because you cannot do every composition with every entailment. But these are validated in the model, which is interesting. And if you think about it, these kind of rules are exactly the presentation of for all and exist as adjoints to weakening functors. Up to the fact that these are not really adjunctions because you don't have dinaturality. The dinaturals compose as entailments. Now, let me just tell you this before we move on to the last part. This is where J comes from. A dinatural like this is the same as a natural transformation with this shape. Hom, P is on this side, P op. You have BA, AB. Y, Yoneda. That's it. And J comes from taking this rule and using twisted exponential to take this part and put it on the other side. And you must invert the variance. This is where J comes from. And J is actually an isomorphism. J is an isomorphism, and J being an isomorphism in the equation of theory is exactly the same as having all the rules for Hom. This is a characterization in this sense. Okay, with these rules, you can do coend calculus, and you can prove these things synthetically. I'm not going to show all of them, of course. I'm just going to show you the first one. This is Yoneda, and you use this kind of Yoneda reasoning using isomorphisms to prove what you want. You start from this. You have ends, which is like a for all. So I can remove it and add a variable in context. You have an exponential, twisted exponential. So I can take this and move it on the left. And then I can use contraction of equality, and I get exactly this. So this says that this part here is isomorphic naturally to this part here. And that's the statement of Yoneda. Co-Yoneda is the same. And then you have other things. This presheaves are Cartesian closed, right-hand extensions, few B for ends, and these are all logical proofs. That's it. So we've seen how dinaturality allows us to talk about directed type theory, not the dependent case yet. Compositionality of dinaturals, that's the interesting part of this. There are some things that you don't get. My claim is that this is intrinsic to cut in the same sense that UIP fails. And just the last thing, what we are working on is to generalize this to the dependent case. So we have a notion of dinatural context extension, and this is going to be hopefully next step to the dependent case. That's it. Thank you.